Okay, so last time we were together, we worked on this problem here, a fairly simple loop problem, and we were looking for a couple of things. We were looking for the current here in the loop, I of t, and we were also looking for the voltage across the 4 Henry inductor. And we got quite a ways through it. In fact, we got to the solution for the current, but I wanted to recap what we did. First of all, by virtue of the problem, it was given that there is zero energy stored, so we know that there is zero voltage across the capacitor initially and zero current through the inductor initially, so we used those. And then I did this, not that you would want to do this both ways, but just to get a familiarity with it. I think as you're working problems, it's always good to try different things and see how those work. But I did it in the S domain here and in the time domain here. So in the S domain, I essentially drew the circuit having already taken the Laplace transforms of it and came up rather directly with that current in the S domain. One thing worth noting, and we'll be using again, is that the voltage across the inductor would be 4, because that's the value of the inductance, times S times I in the S domain. And then I did it in the T domain, which may sometimes to me makes a little more sense, but definitely takes more time writing it in the T domain and then taking the Laplace transform of that expression and getting it into the S domain. You see that we come up with exactly the same thing. So that's good. I think you should probably be comfortable in both of those. Well, another thing before we go is that, again, the voltage across that inductor that we're looking for here, this voltage across here, is given as 4 times di dt. So we'll come back to that. Well, we got to that point, and then we did the inverse Laplace transform. So taking that expression, 160 over s divided by 4.8 plus 4s plus 4 over s, I chose to multiply by s over 4 top and bottom and come up with something that looks a little more like something I want to take the inverse Laplace transform of. I factored this bottom piece and came up with these complex roots, which meant complex solution, which hopefully won't be too bad. We went through that process with K1 and K2, K2 being the complex conjugate of K1, and came up with this expression for the current. We've got the cosine of the cosine of plus theta, theta being minus 90 degrees, which led us to writing it in the sine. So this is the expression for the current in the time domain. Now, that answered this part of the problem here, what is the current, so that's done. But now I want to come back and look at the voltage across the inductor. And I can do that a couple different ways if I want to. I could look at it in the time domain, or I could look at it in the phasor domain, or no, not the phasor domain, but the S domain. So probably the easiest might be to look at it in the S domain. So taking I in the S domain is equal to that expression 40 over s squared plus 1.2 s plus 1. That's what we had. And recognizing that the voltage in the S domain is equal to what? J omega L times I in the S domain, which would really just be 4s times I of s in the S domain. So if I go through that, multiplying it by 4, I would come up then with, if I put this into there, I'd have 160 s divided by s squared plus 1.2 s plus 1. And taking the Laplace transform of that, or the inverse Laplace transform, taking the inverse Laplace transform of that, I would have a fairly similar process. I'm going to have 160 s divided by s plus 0.6 minus j 0.8. The denominator should be the same thing that I was through before, s plus 0.6 plus j 0.8. And I could say then that k would be equal to what? 160 times S divided by S plus 0.6 plus J 0.8, evaluated at S equals minus 0.6 plus J 0.8, which would give me 160 times minus 0.6 plus J 0.8 divided by J 1.6, which gives me 100 at 36.87. So I could say then that writing the expression in the time domain, that voltage in the time domain is equal to 2 times that 100, e to the minus 0.6 t times the cosine of 0.8 t plus 36.87, our step function. So we could tidy this up a little bit if we wanted to. We'd have 200 e to the minus 0.6 t times the cosine of 0.8 t plus 36.87 u of t. So with that, let me double check that. 200 e minus 0.6 t times cosine of 0.8 t plus 36.87 u of t. Yeah, I think that is good. And we're going to get to double check that answer because I was going to try it also in the t. We have used this. There's the 4s if in the s domain right there. We've used that one. Now I want to come over and use this one. So we'll have to practice up our differentiation. So let's do that. And I can say then, page 4, let's try that v of t is equal to L di dt. So we'd have 4. So I've got 4. And then I have to take the derivative with respect to time of I. What do we have for I? That was that expression that we had finished up with, that 50 e to the minus 0.6 t sine of 0.8 t u of t. So I want to hang on as we do that. Well, let's see. I could say that this was, what am I going to have? I've got a 50 in there and a 4, so I have a constant out in front that's 200, so I've got 200, and then I really just have the product rule, don't I? E minus 0.6 t times a minus 0.6 times the sine of 0.8 t, and then I have to look at e to the minus 0.6 t times the cosine of 0.8 t times 0.8. Okay, so let's see, both of them have an e to the minus 0.6, so I've got 200 e to the minus 0.6 t times 0.8 cosine of 0.8 t. I've switched the order there. Minus, kind of protecting that negative sign, 0.6 sine of 0.8 t. And I'm going to have, that dropped off the u of t there. There we go, u of t. So let's see, I need to try and tidy that up. I could say that that was 0.8 cosine of 0.8 t minus 0.6 cosine of 0.8 t minus 90. Putting that into phasor form, 0.8 at 0. minus 0.6 at minus 90 gives me 1 at 36.87. I start to like numbers like that because I can put this back together then, and I have 200 e to the minus 0.6 t, and then inside the brackets, if I go back into the time domain, I'm going to have the cosine of 0.8 t plus 36.87 u of t. Does that look like what we got over there? Let's check that out. 200 0.8 t, yeah, exactly the same. This would be volts. So probably, I think this one is probably quite a bit easier from a math standpoint. Conceptually, this may not be as easy, but probably quite a bit easier from a math standpoint. So I would probably continue working with the Laplace. But it's sometimes interesting to take a problem, to try it with a different technique, to go back and to see if you can do it in the time domain, particularly when you have an answer. And I think there's a lot of value in taking some of these problems that we've been doing throughout the last few lectures and sitting down and trying them on your own and trying with a different methodology in a different direction and seeing if you can get to that same answer. So I encourage you to keep working on these. Well, we've probably pretty well exhausted that problem. Let's go on to another problem then. And with page 5. So I'll look at this problem here, and I'm going to say that I have a circuit that looks like this. I've got a source here, take 100 volts, put a resistor in here, 10 k ohms, and I'm going to have a switch that can move to 2 positions. So it's not open or closed, it's just in a new position. We're going to say it makes this transition at t equals 0. And we're going to put a couple of capacitors in here. Keep things interesting, make sure we remember our fundamentals. I think that'll work. 5 k ohms. And we can say that this is 0.2 microfarads, and this is 0.8 microfarads. Okay, so that's what we've got. We're going to be charging up those capacitors, and then we're going to discharge those through that 5 k ohm. And there's a couple things that I would like to try and find. I would like to try and find I of t here, and maybe I'd like to try and find V of t, the voltage across the capacitors there. Okay. One thing that I need to be careful of, we've got 2 capacitors, we could put them together. We don't want to forget about the very basic things that we learned a long time ago. When I have capacitors in series, it's like resistors in parallel. So I'll take that 0.2, multiply it by 0.8, product over sum, 0.2 plus 0.8 gives me 0.16 microfarad. So I wouldn't want to fall into the temptation of saying that we have 1 microfarad. We don't, we have 0.16 microfarad. So then we'll assume that these are charged up here. So let's work on that for t less than 0. What's this thing going to look like? We've got this source here, 100 volts. The switch is in this position, and then those capacitors. And I'll think of this from now on as just one capacitor, and that is going to appear as a open circuit, isn't it? So with that, I'll get this voltage across here. I'll say it's positive there and negative there. That's going to be 100 volts, isn't it? So we'll need that, and we'll need to observe that polarity. And then what we can do is we'll move the switch. So now t is greater than 0, and we can do this a couple different ways. We can do it in the time domain. So again, getting that practice. We've got that capacitor discharging through the resistor. So we've got 5 k ohms, 0.16 microfarads. And I could talk about this I of t, right? So with that, I would have the voltage across the capacitor. That's 1 over C times the integral of I of t dt plus the voltage across the capacitor initially, T naught, plus then that's the drop, and I'm going to have then a drop across that 5K, so I'll have 5K times I of t is equal to 0, right? And then I take the Laplace transform of this, so I have 1 over C times I of S over S plus V C at T naught over S plus 5K IS is equal to 0. And I'll make my substitution for this. This I'm really going to say is minus 100, because if I look at the polarity here, I've got something that's like that. So I would end up with the polarity across there like that, and that would be a gain. We've taken drops as positive, so a gain would be negative. So I can say then, solving for IS here, or at least factoring it out, that I have 1 over SC plus 5K is equal to the negative 100 over S goes to the other side, so it becomes positive 100 over S. Okay, so let's see if I can get to this point directly by just looking at it in the S domain. So if I draw this circuit in the S domain, again, t greater than 0, this is just a little different twist on this thing. We're going to have something that looks like this. There's the resistor, and I've got the capacitor, and then I'll just put that source right in there that represents the initial voltage there. Positive and negative, V naught over S, and this is what, 1 over SC, and this is 5K. Resistors don't look much different. So I could say then, doing Kirchhoff's law on this, and now we've got I in the S domain coming around here, we're going to have I in the S domain divided by SC plus what, 5K times SC, no, 5K times I in the S domain, sorry, I in the S domain, and then this would be a gain, so I would express it as a negative because I'm taking drops as positive, so I'd have negative V naught S is equal to 0. Okay. So doing the exact same thing that I did here before, I would have, factoring out an I in the S domain, have 1 over SC plus 5K is equal to V naught, that's that 100, divided by S. So whether you do it this way or whether you do it that way, you come up with exactly the same. So now we're going to take that, and we want to try and do that. That's essentially, I mean, if they were asking us for I and the S, we'd be done, but they're not. They're asking us for I and T, and then we're going to have to deal with the voltage too. So let's take that expression in the S domain. And so I in the S domain, repeating what I had there, 1 over SC plus 5K. So I've got, well, I guess just solving for this, shouldn't I? I'll put this down here. We've got this, and then when I solve for I in the S domain, what do I have? I have 100 over S divided by 1 over SC plus 5K, right? So that'd be a better starting point. Let me start at that point. So 100 over S divided by 1 over SC plus 5K. So what I think I'll do is multiply top and bottom by SC. So when I do that, I come up with 100 C divided by 1 plus 5 is 5K is 5,000, so I'll just say 5,000 SC. Okay. So maybe I'll plug my values in. I could say that this is equal to 100 times, what do we have, 0.16 times 10 to the minus 6, that was the value of the capacitor, divided by 1 plus S times 5,000, as that 1K times C, 1.16 no, not 1.6, 0.16 times 10 to the minus 6, which gives me 1.6 times 10 to the minus 5 divided by 1 plus s times 0.0008. And I think I can clean this thing up a little bit if I multiply top and bottom by 1250. When I do that, I come up with something I like a little better, 0.02 over 1250 plus s. Well, I recognize that. That's easy, and of course it's not a complex answer. So I can say, taking the inverse Laplace transform of this, I of t is simply equal to 0.2. 0.2, I got to get that out of there. Should be 0.02. There we go. 0.02. Yeah. 0.02. E to the minus 1250 t u of t, and that's amps. So we could put it in milliamps and move that decimal if we wanted to. Okay, maybe we should do that. I could say that that was 20 e to the minus 1250 t u of t in milliamps. Okay, so that's the current that we were looking for. We've got that then. Let's see if we can get the voltage across there. And one thing to think about is that the voltage across the capacitor, the voltage across there, would be the same as the voltage across there, because things in parallel are the same. So let's see if we can do that. Let's see. So maybe I'll start a new sheet. So voltage across cap. I could say that the voltage across the cap, if I want to do it in the S domain, would be equal to 5K times IS. Do we agree with that? I think so. Right there in the S domain. Yeah, our current's going down through that, so there's the voltage in the S domain. So I think we're okay with that. So this would then be 5,000. That's the 5K. And then what do we have for I in the S domain? You had I in the S domain as right here. So I'll come back and use that. So I've got 5,000 times 0.02 divided by 1250 plus S, which is going to be equal to 100 divided by 1250 plus S. And let's see, I think I'm okay. I could get this. When I do the inverse Laplace transform on that, what's that going to be? Taking the inverse Laplace transform of this, we would get that the voltage in the time domain is going to be equal to 100 e to the minus 1250 t u of t. So that works. Of course, we're going to put the units of volts on there, but we could try it a little different twist. What could we do differently? Maybe we're okay with that. Could we do it in the that was in the S domain. Could we do it in the time domain? Let's see, we found I of t. Oh, we could say it was I of t times 5k, right? So that wouldn't be too bad. So looking at this, if I've got this I of t, I could say that this is V of t, right? So V of t would be equal to 5,000, that's 5k, times I of t. Do I have a value for I of t? I think so. So I want to use consistent units, so I'll use 0.02 e to the minus 1250 t u of t. So what's that turn out to be equal to? Let's see, 5,000 times 0.002. Yeah, should be 100, I think. I'll double check that. I'm pretty sure that is. Yeah, good. So we've got then 100. And I've messed this up a little bit. I've made my substitution for this piece. Goes right in here for I of t, right? So when I multiplied that, I've got the 100e to the minus 1250 t u of t. So 100e volts. So lots of different ways to do these. Whether you do it in these other answers in terms of the S or the T. Usually what I do is try the way that's the easiest, and if that gets too difficult, then I look at going in the other direction. So a good problem there. We've got, in the end, we solve for this current, and we also solve for this voltage. Let me double check my work here. I think we're good. Okay, so moving on, I have one last problem that I want to tackle today. Problems are getting a little more complex. What this problem is we're starting to look at multiple equations. So let's say that I have a problem that looks like this. I'll have a couple of sources here. Say that I have 5 amps and I have a switch here, and it's closed initially. We're going to open it at time t equals 0. And we've got a capacitor, and then an inductor, and a resistor, and a resistor, and then another switch that we're going to close, and a voltage source. So 15 volts, 5 amps. This is opening at t equals 0. This is closing at t equals 0. This is 15 ohms. This is 3 ohms. This is 1 Henry. And this is 1 farad. I guess to keep our numbers easy. Okay, in a practical sense, we wouldn't want to try and short out a current source like that, but I guess since we're working on paper, we can do that. That would not necessarily be a good idea to do that in real life, trying to short that out. Well, I think what I would like to do, we're going to keep this problem easy initially and say that we're going to assume no initial energy storage. Okay, no initial energy storage. So I can go right to the circuit with the switches in place. This one is going to be open, that one's going to be closed. So the circuit should look something like this. I might draw it just a little bit larger because I'm going to annotate it with some currents and voltages. And in a circuit like this, in the past when we had multiple sources, we started to realize that we needed some better techniques, maybe superposition or node or mesh. We'll probably talk about superposition next time. But for now, let's go visit our old friend node analysis. 15 ohms, 3 ohms, 1 Henry, and 1 farad. Okay, so what I'm going to do is I'm going to reference this down here. I'm going to talk about V1 up here, V1 of t, and then I will talk about V2 of t. So that's a voltage here with respect to ground, with a voltage there with respect to ground. Let me talk about the currents then. I'm going to talk about this as I1 of t. We can talk about this as I2 of t. And I'll talk about this as I3 of t. And I guess I better put the I4 in here. There's I4 of t. So if I look at Kirchhoff's laws, I can come up with a couple of equations. I've got the equation at node number 1, maybe I'll call this my first equation at node 1. So I guess I better give that, there's node 1. And that's going to look something like this. We've got 5 amps, so that'll be 5 U of t, indicating the switch is equal to, that's going in, we've got I1 and I2 leaving, so I write I1 of t plus I2 of t, right? Then I'm going to do the same thing. Equation number 2 is the equation at node number 2. So when I write that, I've got I2 of t is equal to I3 and I4. Those are leaving, so I've got I3 of t plus I4 of t. And you could substitute that in there if you want to. I think I'm going to wait before I do my substitution. So let me flip the page here essentially and develop that equation there. So looking at that equation, I could say that I've got 5 U of t is equal to, what's I1? I1 is the current through there, isn't it? So I could say that that's equal to 1, that's the value of the capacitance, times dV1 of t dt, right? And then what am I going to, because this is the value of the capacitance, let's be clear where that came from. And then what I'm going to need to do, I've got this I2 that deals with the inductor, so I'm going to have to add to that 1 over L, which L is equal to 1 times the integral of the voltage across that. Well, if the current's going like that, I've got to find the voltage like that, which is going to be V1 of t minus V2 of t dt, and then I should put in the initial current, which is going to be 0, because we had no initial energy stored in this thing. So if I work through this, I could tidy it up a little bit. 5 U of t is equal to dV1 of t dt plus the integral 1 times the integral of V1 of t dt minus the integral of 1 times the integral of V2 of t dt. Just splitting up that integral I think is fair game. So if I take the Laplace transform of that, I have 5 over s is equal to, this will be V1 in the s domain times s plus 0, because remember we'd have that other term there when we do the derivative. When we take the Laplace transform of the derivative, you have the initial voltage, that would be 0, plus then the integration, those are the fun ones. You've got V1 in the s domain over s minus V2 in the s domain over s. So I can continue to kind of clean this up. What am I going to, of course the 0 drops out. multiply everything by s, and I have 5 is equal to s squared times v1 in the s domain plus v1 in the s domain minus v2 in the s domain. And I could group some terms. I've got v1 in the s domain times s squared plus 1 minus v2 in the s domain. So that's probably okay for now. Let me direct my attention then to the other equation, equation number 2, and see what we can get out of that. So I've got that equation right here, and let me work on that one for a while. Well, maybe I better do my substitution back over here, because I've got the circuit I need to see too. So what's I2 going to be? That's just going to be 1 over L times the integral of V1 minus, or V1 of t, minus V2 of t dt. Is that right? Yeah, V1 minus V2. So that's that, is equal to I3. That's the current through the resistor, so that should be pretty straightforward. Of course, I should probably put in here plus 0. We'd have that term normally, but we had 0 energy stored. With I3, there's I3 there, which is going to be what? V2 over 3? V2t over 3. And then finally I4, that one is a little more difficult. I got to find the potential there. So I'm going to have to subtract 15 and add to it V2. So I have minus 15, put u of t there, minus 15 u of t plus v2 of t divided by what, 15? Okay, same thing we've done a lot of times. I find the voltage across this by subtracting 15 and adding v2, and then I divide by the value of the resistance. So now that I have that, maybe I'll use some space here to go through that. L is going to be 1, isn't it? So get some space here. So I've got 1 times the integral of v1 t dt minus 1 times the integral of v2 of t dt is equal to what? Is equal to v2 of t over 3 minus, let's see, 15 over 15 is 1, so I'll just say minus u of t. And then I'm going to have to add v2 of t over 15. I'm good with that? So with that, I can take the Laplace transform, and I get, I don't have to worry about the 1 in front, so I have v1 in the s domain over s minus v2 in the s domain over s is equal to v2 in the s domain over 3 minus 1 over s, because that's the step function there, plus v2 in the s domain over 15. I double check those. I think we're okay with that. Yeah, I think we're good there. So let me group up some of the terms here. Probably multiply both sides by s, right? And probably, yeah, if I subtracted, when I multiply both sides by s, I could say that I have v1 in the s domain minus v2 in the s domain is equal to s over 3 times v2 in the s domain minus 1 plus S over 15 times V2 in the S domain. Okay with that? So let's say if I get all the V2s on one side, so I could say that I have, so I put all the V2s on the right, so I have V1 in the S domain plus 1, moving that to the left-hand side, so I've taken care of this, and I've taken care of that. Then I've got that's got a V2 in it, that's got a V2, that's got a V2, will become positive on the other side, so I'll put that over there and factor those out. What am I going to have? A 1, and then S over 3, and a S over 15, right? I think that's what we've got. So I think we'll keep working on that. So I've got this one, and I'm going to work on this one a little bit more. So let me do that. Page 10. So let's see. I think I will get, maybe I'll flip sides here, and V2S times 1 plus, let's see, if this were 15, I could say that was 15, so I'd have to have 5S over 15 plus S over 15 is equal to, putting this one on the other side, V1 and the S plus 1. Yeah, I think I'm making some headway now. So I could say that I have V2 and the S times 1 plus 6S over 15, kind of an odd term, but I think that's correct. Take this 1 over here, so I'll have minus 1 is equal to V1 in the S. So that's a nice expression, particularly when I come back and look at it combining with this. I essentially now have two equations and two unknowns, V1 and V2. So the nice thing about the Laplace transform is I can work multiple equations of them. So let's finish this up. I'll make my substitution. I'll go ahead and I think put V1 in here. So I'll make the substitution right there for V1 because we now know what V1 is. So I would have then 5 is equal to S squared times V1. Isn't that right? V1 times S squared and V1. So I'll substitute that in. So S squared times V2S times 1 plus 6S over 15 minus 1. And then I'm going to have just a plain old V1, because we had V1 times S squared and V1. So I will have plus V2S times 1 plus 6S over 15 minus 1. And then I had minus the V2S. So minus V2S. And my only unknown is V2. So I should be able to solve for that, right? So what am I going to have? This turns out to be 5 is equal to, what am I going to get here v2 in the s domain, and then I'm going to have s squared times 1 plus 6s over 15, and then, is that right? So factoring out to v2, yeah, so I think I'll keep that. This s squared, that's going to be s squared times minus 1 is minus s squared. So I think I'll put that over here as a s squared. Okay, so I've taken care of that now. Then here, I got a v2 there, so I think I will open this bracket back up. Okay, so with a v2, then I'm going to add to this what? 1 plus 6s over 15. And then I have to subtract this 1. Right. Yes. That made negative 1 there. I think I'm okay. Did I get that right? So s squared goes out on that one. Then I had this. Okay, so this is v2 times that. So this has the v2 in it. This is just minus 1. So that's going to come over here as a, I'm going to add to that positive 1. And then this has essentially v2 of s times 1. So yes, I think I'm okay with that. Good. So I better, let's see, if I got 1 and 5, that's 6. So I have 6 plus s squared is equal to v2s times, what am I going to have here? This is s squared, and that's s squared, but this is 1 minus 1, so I get to cancel that out, don't I? Yeah, that'll be kind of interesting. S squared plus 6s cubed over 15 plus 6s over 15. Yeah. Okay, so now for v2s, I have 6 plus s squared divided by, could factor an s out of this, of s times 6/15, and this would be s squared, so I have 6/15 s squared plus s plus 6/15. Okay, so that would be v2. Could probably do what? Multiply by 15 over 6. Is that right? Yeah. So 15 over 6 and 15 over 6. When you multiply by that, you come up with what? 2.5 times 6 plus s squared divided by s times s squared plus 2.5s. Is that right? Yeah, 2.5s plus 1. Then we can factor that one, couldn't we? This is fun. We'll just keep going. I think we're getting close, though. So we had that V2 in the S domain was equal to 2.5 times 6 plus S squared divided by S times, and I should be able to factor this term down here. Looking at the factors of that, I'm going to have what? S plus 2 and S plus 1/2, is that right? Yeah. So that would be our answer in the S domain for 2. Then you, of course, could take the inverse Laplace transform and come up with it in T domain. I'm not going to keep beating that that horse, so to speak. I'll let you do that if you want to. I think if we go ahead and get V1, the object of this problem will be satisfied to work the multiple equations. So let's go see if we can get V1. Do we have that expression for V1? If I go back here, V1 right here. Okay, so I'm going to take that expression and use that to get my V1. So V1 in the S domain would be equal to V2, which is this thing, right? 2.5 times 6 plus S squared divided by S times S plus 2 and S plus 1/2. And then I need to multiply that by what? 1 plus 6S over 15. And then I need to subtract 1 from that. And that is my V1. So let's see how that works out if we finish that up. If I get a common denominator, what am I going to have here? I'm going to have 2.5 times 6 plus S squared times 1 plus 6S over 15. And then I have to subtract off S times S plus 2 times S plus 1/2 divided by then the common denominator S plus 2, S plus 1/2. And when we work all of this out, this piece here, when you multiply that all out, what are you going to come up with? I think we'll come up with what? 6S squared. Yeah. So you've got 6 plus S squared times 2.5 plus S. Is that right? Yeah. Minus S times what we have before, S squared plus 2.5S plus 1, S squared plus, I'm kind of running out of space here. Give myself some more room. Okay, so I'm going to have 6 plus S squared times 2.5 plus S. Yeah, when you multiply 2.5 times that, and that tidies up. 2.5 plus S and minus S times, when you multiply those together, that's what we factored initially, S squared plus 2.5 S plus 1. And this turns out to be 15 plus 6S plus 2.5 S squared plus S cubed, and what, minus S cubed minus 2.5 S squared minus S, which turns out to be 15 plus, those cancel, we'll have 6S minus S, 5S. 15 plus 5S. So I've got then that V1 in the S domain would be equal to, this was just the numerator, so that turns out to be 5 plus, so I could actually even factor out a 5 out of that, couldn't I? Really get sophisticated here. So I have 5 times S plus 3, that's good. 5 times S plus 3 divided by, then we need this S plus 2, S plus a half. So that would be my answer for V1. Double check that, 5S plus 3, S plus 2. And my answer for V2 up here. So those would be my final answers. And that's in the S domain. Double check that. Yeah. So you could take both of those and do the inverse Laplace transform of them if you wanted to, the partial fractions. I'll leave that to you. But I think, again, the purpose of this circuit was seeing if we could work multiple equations, doing essentially a node analysis where we had equation 1 and equation 2, and we had to work those simultaneously. We'll try in the future a problem where we maybe use superposition on this and see how that works, and that should also work. So hopefully that was a good exercise. I encourage you to pick up these problems and to try them out. See if you can do them differently, do different substitutions, and see what you come up with. Take care till next time.